Why is the sky blue? Well, if you look it up, AI will tell you that blue light scatters more, and the explanation is Rayleigh scattering, and this relation between the intensity and the wavelength of light. But that's not enough of an explanation. To know why the sky is blue, you have to know how the light is being scattered. The sun emits all kinds of light. In the visible range, it's actually violet that has the shortest wavelength, but the sky appears blue because the sun emits less violet. Also, the human eye is less sensitive to violet, and some violet is absorbed by the upper atmosphere. The range we're concerned with is visible light, the light we can see and interpret as color, which is about 700 to 400 nanometers. But what does a wavelength of light even mean? Light is electromagnetic radiation. It is alternating electric and magnetic fields that are oscillating perpendicular to each other, with energy traveling this way. If this sounds complicated, it's because it is. The wavelength is a length of a full electric field oscillation. This is how you should imagine light, using the wave model. Really take this in, because this is essential for understanding why the sky is blue. Light is electromagnetism. Okay, if we had no atmosphere, the sky would be black. When light scatters through our atmosphere, Rayleigh scattering occurs. This happens when the particles are smaller than the wavelength of light. The air, mostly diatomic nitrogen and oxygen, is formed by small molecules, about 0.3 nanometers in size. Because the particles are much smaller than the wavelength, the electric field they experience from the light is essentially uniform. And since the wavelength is much larger, the particles are point-like, isotropic, polarizable objects, which is a technical way of saying they are just like tiny, uniform spheres. The shape doesn't matter because they're so small. What does matter is that when they're in visible light's electric field, the electrons, which are negatively charged, move one way, and the nuclei, which are positively charged, move the other way. This is called a dipole moment, a separation of a positive and a negative pole. We have a single dipole, and one moment the charges are accelerated one way, and the next, the electric field is flipped and the charges are accelerated the other way. This is one oscillation of the dipole. For blue light with a wavelength of 450 nanometers, the frequency is about 670 terahertz. So the charges in the dipole will be changing direction 670 trillion times per second. This is an incredibly high acceleration. They're just not traveling very far. But that brings us to a core principle of electromagnetism. An accelerating charge produces electromagnetic waves. This is why the light scatters. As the charges accelerate, they change the electric field. Imagine this is a charge. This wave, the update in the electric field, travels at the speed of light, which is not instantaneous. This changing electric field produces a magnetic field, and a changing magnetic field produces an electric field, and thus we have an electromagnetic wave. As the dipole oscillates, electromagnetic waves re-radiate out from the charges. And importantly, the charges are oscillating at the same frequency as the incident light. Energy is not being stored in the molecule. Light is accelerating the charges, and these charges re-radiate the light. It's an elastic process. So these concepts of electromagnetism help us to explain why the sky is blue. The sky is blue because of Rayleigh scattering.